To start out section 8.3, estimating a mean, we're going to do an activity called Calculator Bingo. In this scenario, we suppose a farmer wants to estimate the mean weight in grams of all the tomatoes grown on his farm. To do so, he will select a random sample of 4 tomatoes, calculate the mean weight in grams, and use the sample mean x bar to create a 99% confidence interval for the population mean mu. Now recognize, of course, that if the farmer was doing this, he wouldn't already know the mean and standard deviation of his tomato plants because this is what he's trying to estimate. But for the purposes of our simulation, suppose that the weights of the tomatoes on his farm are approximately normally distributed with a mean of 100 grams and a standard deviation of 40 grams. So we're going to use our calculators to simulate taking a sample of 4 tomatoes and creating a confidence interval. So first of all, we should always check conditions. Are the conditions for making a confidence interval satisfied? Well, we have a random sample right here, random sample of 4 tomatoes, so random condition is satisfied. We're doing a sample of 4 tomatoes, which is certainly less than 10% of all the tomatoes in his field, and it says that the population of tomatoes is approximately normally distributed, so that means the distribution of sample means would also be normally distributed. So we have satisfied the conditions. So now I'm going to go through some of the instructions here. I'm going to open up my calculator. Now I want to point out that I did random seed here. Well, first of all, the very first instruction is to create a list and call it samp. And that's my sample will be stored in there. Now, let me just explain what some of these things do here. Random seed just establishes this number. There's no significance to this number. If everybody in the class puts in a different number, we'll all start in a different spot in our random number generator, and that's important. Random normal, 10, 40, 100, mean of 100, standard deviation of 40, sample size of 4. So this generates 4 random tomato weights that would come from a normal model with that mean and that standard deviation. Then we can take the mean of the random normal of all of that, and that would give us the mean tomato weight. We could take then that mean plus or minus, this is how you do plus or minus in the calculator, the critical z-value times the standard deviation of the population divided by the square root of 4, and then this would give us a confidence interval. But we want to generate lots and lots and lots of these in one step. So here's what we're going to type in. We're going to type in mean, random norm of 100, 40, 4, and we're going to store this to the sample, to the list samp, which I can find under my variable. Okay. Now, I want to do a second command on the same line, so I'm going to go into this little button here that has some different kind of punctuation marks. I'm going to put a colon there. That allows me to add another command right below this, and now we're going to say mean of samp instead of mean of all of that other stuff like I did up before. So I've created a sample of 4 tomato weights. I've stored it to the list sample. Now I'm taking the mean of the sample, and then will be plus and then negative 1, 1. So that's our plus or minus times, and we got the 2.576. That's the one that would give us a whatever confidence level was that, 99 that we wanted. I think it was 99 times 40 divided by the square root of 4. Okay, and this will give us, oops, I have something. Okay, got to pause here and find out what I typed in wrong. I figured it out. I wasn't supposed to put mean of random norm and store it to sample. I was just supposed to do random normal and store it to sample and then take the mean of it. So there we go. So I've got my random sample of 4 tomatoes, take the mean of it, plus or minus the critical value times the standard error, the standard deviation. Okay, so here is my interval. Now, how do you play bingo? Everybody in the class is doing this, and we're going to just keep pushing enter, and every time we push enter, it does this again, and we get a new confidence interval. And the true population proportion of the tomatoes has been given already as 100. So our interval should capture the true population proportion. It's a 99% confidence interval. But if it doesn't, I want you to yell bingo. So we're going to just do this a few times, and we're going to see if we get one that doesn't capture the true population proportion. Okay, go on here for a while. Ooh, that one was close. Oops, did I miss one? Nope. Hopefully, oh, I missed one right there. That would have been a bingo. Bingo right there, because that one's all above 100, so there's a bingo. Okay, so we're going to keep going for a little while longer. It's hard to spot these, at least for me. I got old eyes. Let's see here. Well, you can see most of them seem to be capturing it. And it turns out when we do this activity in class, there's long periods of silence with occasional bingos. That's kind of what happens with this. Okay, so now we're going to go back and we're going to make a little change. Okay, so we've done all this. What if we don't know the population standard deviation? Which we usually don't, because if we don't know anything, if we're trying to estimate the mean, how in the world would we already know the standard deviation? So I guess you probably would say, well, what would we use instead of sigma? Well, we're going to have to use the sample standard deviation, S of x. Okay, so we don't know the population standard deviation, so let's use the sample standard deviation in place of sigma. So we're going to copy and paste the command in the calculator and change the 40, which was the population standard deviation, to standard deviation SAMP, standard deviation of the sample of SAMP, which has our 4 tomato weights in it. And then we'll play bingo again. So going back to my calculator. Okay, so I'm going to go up and copy this, and right here for where 40 is, I'm going to change this to standard deviation SAMP. Okay. Okay. So now, instead of putting 40, it's going to put the standard deviation of whatever my sample is. And I'm going to play bingo again. Remember, anytime it does not have 100 in it, I'm going to yell bingo. Oh, bingo. Let's see here. Bingo. There's another one. Bingo. See, these ones are fluctuating all over the place. Well, this isn't showing a super good example of this, because in class when we do this, we get a lot more bingos. Make sure I did this correctly. Nothing like showing, let's see. Oh, I've done it correctly. So anyway, when we do this in class, we find out that we hear a lot more bingos than we did before, although the ones I'm doing certainly aren't giving good examples of this. And so we find out the first time we did it, we had a 99% confidence interval, and we would only expect to miss the true population proportion about 1% of the time. 99% of our interval should contain the true population proportion. That's what 99% confidence means. But we find out when we do this with the sample standard deviation instead that we have a lot more misses. So why is that? Let's examine this using an applet. I need to figure out how to pause this baby here. Okay, so let me get my little screen up. There we go. Okay, we've done an applet similar to this before. I've set this up to do means from a normal model. So sample means from a normally distributed population. We're going to do a z-critical value with sigma, which means we're using the sample standard, or we're using the population standard deviation. So here's my mu, my sigma, and my sample size. I'm going to do 100 intervals, and we're doing a 99% confidence level, so we should expect about 99. Oh, that's exactly 90. We only got one miss in 100 samples here. So let's do another 100 samples. Okay, didn't even get any misses there. Got one miss every 100 samples. So there's one miss, one miss. There's three misses. Of course, we had a couple with no misses. So we're averaging out about 99.2% of our intervals contain the true population proportion. So it's about what we expect. Okay, so let's reset this now. And instead of using the z critical value with sigma, we're going to use the z critical value with s. That's the standard deviation of the sample. So I'm going to do the same thing. I'm going to see what we get here. Okay, notice here all the misses we got. And look at the size of the intervals. Some of them are pretty long and some of them are really short. The size of the intervals vary quite a bit, and those shorter intervals we're getting a lot of misses. Look at all the misses we're getting. We're nowhere close to 99%. So why is this happening? Why is this happening? Okay, so let's go back and talk about why is this happening. Okay, so here's the one interval we used. X bar, our sample mean, plus or minus 2.576 times 40 over the square root of 4. And this is where we got 99 confidence that looked good. Here we have x bar plus 2.576 times standard deviation of the sample over square root of 4. The intervals were too narrow. We had lots of ones that missed. Well, it turns out that the standard deviation of a sample is almost always smaller than the standard deviation of a population. Think about it. In an entire population, you have a largest tomato and a smallest tomato. And when you put the largest and the smallest in with all of the other tomatoes, you have a fairly large standard deviation. But in a sample of size 4, it's highly unlikely that I would get either the smallest or the largest in my sample, much less both. So my standard deviation of my sample values is going to be almost always smaller than sigma. So we noticed there was a lot of variability. Maybe I got 4 tomato weights that all happen to be kind of close together in size, just randomly. And then I'd have a really small standard deviation, which would create a really small interval, and it would miss the true population mean. So that's what was happening. So what do we do to fix this? Well, it turns out there is a way to fix this. There is another distribution called the t-distribution. So let's check out the t-distribution. Let's reset here. And so if we take 100 samples using the t-distribution, 100%, 100%, 100%, oh my gosh. Oh, there's 2 misses, 100%, there's 3 misses, 100%, 1 miss, 1 miss. Notice that we're averaging 99.2% hits for a 99% confidence interval, just like we did before when we used z with sigma. So this seems to have fixed the problem. So it's this mysterious this t-distribution that seems to be helping and giving us what we need. And so in our next video, we'll talk about what exactly is a t-distribution. So leaving you hanging for right now, have fun.